Alright, so viscosity of monoatomic gases, right? Momentum transport. So Chap Chapman and then Enskog did a lot of work, and they've seen that if they're trying to find the viscosity of monoatomic gases, right, there's an equation that we can use to do that, right? And it says that if we only end up getting what do you call it, the viscosity in poise, right? We only get this when here is a molecular mass, which is this. We only get that when the molecular mass is in gram, right? And the temperature T is in Kelvin, right? And then this what do you call it, parameter here is in Armstrong, which is basically 10 to the power minus 10 meters, right? You only get it. You only get the viscosity in poises when these values are having a certain unit. So you must always pay attention to the unit, right? And we're just saying that for the collision integral is actually gotten from this, right? So it means that this collision integral here, this here, is the same as this Boltzmann constant temperature on this parameter, right? Energy parameter, which is what we see here, right? And then if you are using tables, these values should be given, right? If you are using table, this value should be given. So it's saying that we are only able to find the viscosity in poise when this parameters, which is the m, right, the molecular weight, the temperature, and then this one here, this sigma here, are having this particular unit. So if you want to get this in poise, it means that you must get these parameters in the unit given here. That's what I say. So here, what happens is that we are going to use these tables to solve an example, right? So here, the example we have is saying that let's see, we're trying to find the viscosity of hydrogen, right? And clearly we know that hydrogen gas, which is this, right, is monatomic. Why? Because the only atom involved is hydrogen, right? So this particular what you call equation can be used to solve this one, right? And here, because of how we are doing it, pressure is not taken into consideration, right? We are seeing 180, meaning that the density is not high, right? And there's the temperature here, so we are going to go about it. So it says that the viscosity is equal to 2.67 times 10 to the power minus 5. Is that right? 6.27. 2.67. Yeah, 2.67 times 10 to the power minus 5. And then we have square root mt at molecular weight, temperature, and then the sigma here, the diameter, and then this collision integral, right? Okay, so clearly we are going to go through the table and see the parameters that we have, right? So we have the temperature here. We have the temperature directly from the problem, right? We have the temperature to be in 1364 Kelvin. Very important, Kelvin. It's been specified already, right? Since in Kelvin we don't do any conversion, right? And then the molecular weight for hydrogen, right? Let's see what we have for that. We have this. So there's the hydrogen we are talking about, right? Yeah, the hydrogen gas, and the molecular weight for that is 2.016, right? So I mean the m is equal to 2.016, and then we need this, right? We need this square, right? And for hydrogen, we know that the characteristic diameter to be what we have here. So you see, it's having it in angstrom. So remember that if it's not given, then you must convert because the equation already specified the unit, right? Yeah, it's not given this, so they must convert. So we have it to be 2.827, right? So this will mean that 2.827 squared will give us this. The only thing that we don't know here, and the last thing we need to be able to find that is this, right? Right. So let's see. So it's very important that you understand the concept. The unit is very important. It may seem subtle, but it's very, very important. So you know what the equation requires, and if there's any trouble, you convert and you do what you're supposed to do, right? So now we know what the parameters, and then we're just trying to find the characteristic diameter, right? So that will be 2.8827 squared, right? And that gives us let's do 4 dB, right? 7.9919, right? And then we know here, as a matter of fact, this grams per mole, right? If the units are checked, and here we have what angstrom squared, right? This squared, right? So clearly everything has been given. The only thing we need now is the collision integral, right? And then we know this is actually this proportional to kb on this what do you call it, energy parameter times temperature, right? Okay, so that's what we're going to do. So for hydrogen, this parameter has already been given, right? But let's see what's happening. So when we look at this table here, what happens is that we have it in something similar but different, right? So you see it has been inverted, right? Yeah, so it's the same thing but inverted. So that means that for us to put the value there, what we have in the table is this on K Boltzmann constant, KB, right? This is not K and a B, it's just Boltzmann constant. So this was given in the table. So that will mean that we have to invert that. That will be 1 on the value that we have there, which is this on KB. And then we just multiply by the temperature to get this collision integral, right? So that's what we're doing. So moving on, this is what we do. We have 1. The value for that, the value for this from the table is what we're going to check now. What did we get? We have this is it. We have 59.7, right, for hydrogen. So that will be 1 on 59.7. And the temperature we have from the problem is 1364, already in Kelvin. So we don't convert, right? So that's what we end up getting for this collision integral. So let's see. That's 1 on 59.7 times 1364. Right, so that's what I get. We are getting 22.84, let's say 7. It has already been stated that this is a dimensionless quantity, right? So this has no unit, so no unit. But whenever there's a unit, you write it just for understanding, right? So just for clarity. So this has no unit, right? But then in order for us to be able to find the viscosity, that's the equation, right? We need M, we found that. We need temperature, we found that. We need this, we found that. We need this, we found that, right? But then we are saying that this one here is actually a function of some other parameters, right? Okay. So that will mean that now that we have that, we have to go through the table, right, to be able to find the actual value that we need, right? So what we found now is just this. So this means that it's proportional, not actually equal to, right? So we are saying it's proportional to this, right? So now that we found this, it's not that it's the same. Now that we found this here, which is this value here, right? Which is this. So in order for us to correct what we've done, this is not the collision integral. That's actually what's the name? The KBT on the energy parameter. That's actually this. But we are seeing that this collision integral is proportional to this. Right? So that's what it means. So this whole thing is proportional to that. Now that we found the value for this, we should be able to find the proportional value for this. So that's what it's saying. So we are going to the table. We have the KBT on the energy parameter, right? So we have that, and then that for that we have what's the name? The 22.84, right? So that's where we do something we call the extrapolation. So we are going to go through it and see what's actually happening. So we know that for that value that we are looking for, that's 22 point something, right? Will be about here. So let's use something that we can see. Minutes, okay, right. So we know it's 22 point something is about here. Right. So it's actually somewhere. So we have this KBT on this, right? Yeah, we have that, and then it's actually, you are saying this is proportional to this, right? So that will, this value will help us to get this, right? So let's see. And the value that we have for this one here is in between these two values here. So that's what we do, what we call the extrapolation, right? So we are going to go through it and see what it means. It's just words for something quite simple in this case, right? So that will mean I will be considering this side, right? So now we are going to write that out. So let's see. So that's okay. KBT, let's write out. So we have K, Boltzmann constant, temperature, and this, right? Versus what's the name? The actual collision integral, right? Which we are trying to find. The last thing we need to find the viscosity. This, right? Okay, and this smaller. All right. So we have 20 here, and then we have about 40 here. The value that we are looking for is this. The value, we have this one here, which is this. So it's under this side. So you see, we have this, and then we have it here. So it's under that side of the table that I'm doing. So we have 22.8476, right? And then for the 20 here, there was a value that we had. That's on the table. We have what? 0.7432. Right, so that's for the 20, 0.7432. And for the 40, you have 0.6718, right? 0.6718. So that means that what we are trying to find here is this, the value that we have here, which we don't know. And we need that to be able to find the viscosity, in this case, of the hydrogen gas, right? So let's see. And so this is what the extrapolation is saying, right? This is what it means. So when we come to this graph here, you see that what's happening is that, let's see, this value here 8, sorry, this is 6, 8, 10, 20. So basically this means that as you are going down for this particular size, you are going down, the value is what? Increasing, right? And for this side here we have this, so you see it's decreasing. So that means that as you are going down, right, for this particular one, the value is what? Decreasing, right? So that will mean that if we are to plot them on a graph, so let's see, I put this one on the x-axis, right? So if I am to plot a graph like this, where I put this k, you're just trying to see what the extrapolation is saying, that big, the term, right? KBT. If I put this one on the x-axis and I put this one on the y-axis, the collision integral here, what it says is that as one is increasing, the other is decreasing, right? So as this x here, this one here, as this one here is increasing, the other is decreasing, right? So that will mean I have what? A negative slope. So it will be something of this sort. So it's a linear, what do you call it, relationship between these two. The relationship between these two is linear, right? So that will mean that we can find what? A slope. And if we can find a slope, that's when we can play with the extrapolation something. So that will mean that we have a slope which is constant. The slope is constant. So that will mean that, let's see, the change in x over change in y over change in x is constant, which is the slope, right? So let's see. That will mean that from the graph that we draw, the change in the x component over the change in the y component is what? Constant. And in this case, it's changing y over changing x. The change in y over change in x is constant, right? In this case, we have this to be our x. I'm choosing it that way. You can choose anything, but it should work, right? We have this one here to be our x, and we have this to be our x, and we have this one here to be our y. Let's just understand. If you are solving, you can skip everything that we are doing because you understand what you are doing. So that will mean that whenever you pick any of these values and then you find the difference, you get it's a constant value. So all what this means is that if I pick two values of y, two values of x, their corresponding x, and I subtract, I do the ratio, it should be constant throughout. So now this is what it means. Meaning that if I pick, let's see, our aim is to find this, right? So let's make here y, right? So that will mean that if I pick, where's the y's? Right, this side is the y, right? So that will mean that if I pick this and I pick this, right? In this case, to make our work easier, the top one is the one we are subtracting from. So that will mean that if I do 0.7, let's take it to this side. If I do 0.7432 and I subtract this y from it, right? Because here is y, other side is y, other side here is y, right? So if I do a difference in the y, right, I subtract this one from it, that's 0.6718, right? And I take the corresponding x. So where's the corresponding x? This for this, right? we are seeing this x, right? So if I divide it by this, the corresponding x for the 0.7432 is 20. The x for the 0.6718 is 40, right? We are saying this is constant. So this will mean that if I pick these two and I do this for them, I can do something else, and it should be, the slope should be the same, right? Because we've seen that if we plot these two, we have a linear graph, and then the slope is constant, right? So that will mean that if this time around I pick these two as my y, right, and I pick these two as my x, I can equate it to this one here. So that's what we're going to do, right? So for the y here, so clearly we know that these ones are y, these ones are x that we've subtracted, right? Yeah, so now I'm going to do the same thing here. This is the y, right? So that will mean that have what? So you see the convention that we use, top one is the one that we subtract from. So y minus 0.6718 is minus, right? The corresponding x, we have 22.8476. Let's make this smaller. Oh, it's fine. Minus 40, right? So that will mean that this is constant, right? So that will mean that this side should be equal to this, and therefore we can find our y. We have an equation that we can find our y. So that's what it means when we do that. So even if you forget this, know that it's a linear relationship, and then we can do that to find what we are looking for, right? So let's see. So we have let's see, trying to solve this. Okay, so we have 0.7432 minus 0.6718. Bottom we have 20 minus what? Let's see. So here the calculator I'm using accepts only x for variable, right? So I'm going to give this x and solve it. It doesn't mean it's actually x, right? So I have using x to place this in the calculator, so it gives me the value 0.67, right, 18, and at the bottom we have 22.8476, right, minus 40. So let's see what we have for the y, which in this case we typed it as x in the calculator, right? This is what we have. So we have the y to be 0.733. Let's do 40p, 730, right? And in this case we know that it will be something for this, right, which is the what do you call it, collision integral that we're looking for. So therefore the collision integral that we are looking for now to finish this problem off will be 0.7330. That's what it means. That's all. So now we can put everything in and be able to solve it, right? So we have the viscosity of the hydrogen gas, right? Let's make it this way. So that's 2.67, right? 10 to the power minus 5, right? And we have minus 5, right? And then we have a square root, molecular weight, temperature, right? And then we have this characteristic diameter squared, and then we have the collision integral, which we found just now. We want to put everything in. So we have 2.67, right? 67 times 10 to the power minus 5. And we have times square root, times square here, and the molecular weight we was given, we found that from the table to be 2.016, right? And the temperature was one, already in Kelvin, 1364, right? And then this characteristic diameter, we squared it already, we had 7.9919, right? And then the collision integral we just found to be 0.7330, right? So that gives us the viscosity of the hydrogen gas in this case to be 0.00023900. Let's just write it. We can do the conversion there, right? And because we use the unit per the equation, we have this to be in what? poise. Very simple, right? So that will mean that this is the viscosity. It's minute. So this is the viscosity in poise. And then remember, you can be asked to find it in any other unit, right? So if you have it in this way, so let's see. If you want to make it bring some numbers, so let's see, 1 2 1 2 3 4 5 6. So let's see, now we have it in poise, right? We have it in poise. Let's see, what if we are asked to make it in a centipoise, right? We know centipoise, the centi there is 10 to the power minus 2, right? So that will be, that will mean that we'll have to multiply this by this, so we'll get 0 points. Let me get 0 point, right? 0 0.0. I mean, we get 0.0239. If it's 4 dp, 0 centipoise, right? Yeah, centipoise. And if we are asked to make it in Pascal-seconds, right? So the units are very important. So I'm asked to make it anything, but remember, because we use the equation, what we actually get will be in poise, right? But when converted to centipoise, this is what we get, right? Centipoise is what we get. If you want it in Pascal, Pascal-second, that will be, right? So we divide this further by 10, so that will give us 0.239 Pascal-second, right? Because we know that 10 poise is equal to Pascal-second, right? And we know that what's the name? 10 to the power, so that's 100 centipoise is equal to poise, right? So this 10 to the power minus 2 takes care of this, right? So that's what it says. So if we are trying to convert this to the Pascal-second, so you can do the conversion straightforward, right? This is 10, just introduces this Pascal-second, this just 10. So if you are taking it, that will mean that we just have to divide through by an extra 10, right? So that's why we divide through by an extra 10. So that's 1 2 3, yeah, 0.23. Yeah. So that's it. Let's see. So remember the unit in the equation, right? The unit that must be used, you have to use the equation and the conversion units, and then we find, right? So we can even convert this further and say that we have let's see, 239, right? That means that we've moved 1 2 3, right? And that will be milli, right? That will be milli Pascal-second. It depends, right? So, which is the same as 2.39 times 10 to the power minus 3 Pascal-second. So it depends on the unit that you asked to find the tenet, right? So this is what we have. All right, that's it.